All right, I think we're getting started here for our control systems lecture. All right, how are we doing this morning? Good. Glad to hear it. You're present. That is step one. That is step one. All right, it's good to have you here for design and analysis of control systems. That's what you should be here for. Okay, when it comes to this class, it's an undergrad and graduate class. So who here is currently registered for undergrad? Who's here for graduate? Okay, yeah, pretty good mix, pretty good mix. So this is for both of those courses, and you'll be here, okay? All right, so welcome. We meet Tuesdays and Thursdays, not at that time, at 9:30. I accidentally changed it at the wrong time. So 9:30 a.m., we'll meet here. It's a face-to-face class. We'll be teaching out of the Control Systems Engineering book by Norman Nyes, okay? My office hours are currently posted. My office is right upstairs in this building, okay? AME 217, okay? Monday 3 to 4, Thursdays 2 to 3. I might be changing that depending upon later schedule, but I'll always let you know. We will be delivering this information on Canvas. The course is not yet published for your viewing yet, but will be in a couple hours, and you'll see an announcement for that. Zhuwei Wang is your TA for this class. All right, so that is your introduction. And question is, who am I? I'm Christian Hubicki. Okay, I'm an associate professor of mechanical engineering here at the FAMU FSU College of Engineering. I think this is my 8th or 9th year here at the college. I work in robotics. That's my field of specialty. In fact, my lab is just right down the hall with our robot lab. Okay, and the thing is, I've taught controls for a while now, and I've come to really like it. Makes sense. It's my field of study. Okay. All right. For our syllabus, it'll be posted to our Canvas site. But here is the grading breakdown. Okay. 20% quizzes, 20% homework. You get 2 exams, and there's a final group project. Okay. Final group project. Typical grading scale here for the college: A, B, C, D, and F. We don't talk about those letters, though. We don't let them enter our minds, those last couple. Okay? All right. So here's your textbook. It's Control Systems Engineering. That's an important textbook. I'll be assigning suggested reading before each of these lectures. There's going to be a course schedule online on the Canvas page. I like to have a big table, which is like, this is what you should expect for every lecture and what all the readings are when that gets posted later today. I also have some additional online materials for the class. So this is the textbook that we are working with. So, all right, this is a face-to-face course, Tuesdays and Thursdays, face-to-face. However, I do like to do select online lectures. Who here has taken a course with me before? Handful of you, handful of you. Sometimes for some of those classes, it's 50-50. 50%, like we'll do a lecture here, then a lecture remote. And the reason why is I like to do coding lectures. And often that's really great. I have a home streaming setup, which I'm sure surprises you based upon what you see here today in front of you, right? Where I can do and pull up lots of things, lots of good coding things, and you can be at home and you can code along with me. I like to do that, and we'll probably do that a couple of times throughout the semester, but predominantly this will be face-to-face. We are recording all the lectures and placing them online, okay? In fact, assuming that I can't check my streaming status right now. Hopefully it's working. Let me check real quick. Oh, it's working. Oh, thank goodness. All right. We are streaming live to YouTube right now. Hello, YouTube. Okay. I can't see your comments, though. I'll work on that for a future lecture. Okay. And what that means is, yes, you can watch the stream live yourself that way if you need to. Okay. I do encourage you to come to lecture. All right. I'll talk to you a little bit more about why in a few moments, but it probably has to do with why we have quizzes and exams. Okay. For the course, there are prerequisites. So this is a senior level, grad level course, right? Our official prerequisite is Dynamic Systems 2. Who here has taken a Dynamic Systems 2 or equivalent, right? Okay. Most of you. Okay. Now, those are the formal requirements. Informally, what I want people to know going into this class, I need you to know calculus, meaning, can you take a derivative? We don't do a lot of integrals by hand. You're welcome. Maybe a couple, all right? Maybe a couple at the beginning, but predominantly taking derivatives. Do you know linear algebra? Now, you might say, oh, I didn't take linear algebra. Oh, panic not, my friends. Panic not. What I mean is, have you ever multiplied a matrix with another matrix? Do they still teach that in like high school? They do? They don't? They don't teach that in high school? Some okay. Okay, they do. So give me thumbs up or thumbs down if you had it in high school. 50-50. Okay, we will cover how to multiply a matrix, all right? It's not rocket science, it's matrix science. Okay? All right? And coding, we will be doing coding. And what I mean by that is, can you write a loop and can you say x equals 2? All right? That's the kind of coding. You don't need to come in like, oh man, I am a pro in Haskell. I don't do anything other than functional programming. Stored variables are for losers. We don't need that. Okay? Anything. Any kind of coding experience, and we'll take it from there. Okay? Informally, that's what you need to know. In case for some reason in your schedule you haven't taken dynamic systems 2. But it is a very useful prerequisite. Okay? Policies. Okay? I do encourage attendance. And look, I've been a student and I've been a professor long enough that I tend to know how this goes because I love recording the lectures. For some reason, I like being on camera. I have no idea why. But and I think it's a useful tool for you all to watch after the fact, right? Actually, make sure I am recording over here. I can't do that. That's all right. 1 second. All right. Sorry, 1 second here. Make sure everything's going right. First day jitters. We're all right. Okay. So, yeah. So, as a result, what will happen is people are like, I want to sleep in. I don't want to be in at 9:30, coming to the AME building. Look, I get it. I like to sleep too, much contrary to popular belief. Okay? And so they're like, oh, I'll just catch the lectures after the fact. I will post you'll have access to the videos after this is up and right now if you're on YouTube, right? Okay? What happens though is people are like, oh, I'll catch up with it later. And then they let one lecture slide by, then another lecture slide by. And then all of a sudden there's a major assignment due and you're about 8 lectures behind. And then you're really behind for the rest of the class, right? So I really recommend it's just come to lecture here. Okay? This stuff is here for your benefit and for your parents who can also now watch control systems from home. But but having in-person quizzes is a way that I try to make sure people are keeping up with the material. All right? Policies, you can't copy work. You can work together as a team. I highly recommend homework groups. You know, for people who that was one of the best things I ever did in college was have a homework group, study group to work together with. It's great for accountability and pushing through problems. Can't copy each other's work though, okay? And that does include copying from generative AI, okay? Now, I will give a longer policy on generative AI, which I'm still drafting up. And my feeling is that it's a computational tool, like we have many computational tools in the class. You know, things that I found that students can find it to be helpful with is helping debug code. That can be helpful for that. It's not bulletproof. Sometimes it can throw you on wild goose chases, but it can be helpful, right, as a tool. So if you're doing a homework and you have to do some coding on it, you're like, oh, I'm hitting this error. What's going on? I can't figure it out. What do you think it is, ChatGPT? And if it points you in a direction you find it, that's great. That's a good use of the tool. It saved you time, hopefully taught you something about what was causing the error. What you can't do, though, is take a PDF of the assignment, give it to ChatGPT, spits out and then you copy the output and say, that's my homework. Because it's not your homework. You copied it. That's plagiarism. Okay? All right? But I'll have a long, part of the job of this class is to learn. And yes, you can, a lot of the time, use these generative methods to solve a problem for you, right? But you do not learn how to solve the problem, okay? All right, so I'll get off that hobby horse, but I'll give you a bit more guidance on that as the assignments come more due, okay? Makeup assignments, I'm not obligated to give makeup assignments. On occasion I have, just when people have fallen really far behind, but I'm not obligated. That's in the syllabus. We were operating off of a Canvas site. All of your assignments will be submitted through Canvas. Your homeworks and all of your final project-related assignments are done through Canvas. That's where all the announcements are coming through. You'll get your emails through Canvas, and that's the official way in which I communicate with you all. All right, lectures are posted and recorded on Canvas at the earliest opportunity. I'll be putting links on the schedule. If you go when you'll see a schedule and you're like, oh, Tuesday, August 25th. Oh, there's a link to the video. Click it there, right? And you can have all the videos there. So you can go back. It's great for studying for your exams. That's all good. Okay. Homework, 20% of the grade. I'll assign it about 2 weeks in advance. Okay. In the past, we've done about 5 assignments per semester. They can be a little on the long side. So a lot of them come out of the book. But I'll try to make sure that you have access to the problems in one form or another. They're going to be a combination of hand math and also coding. Okay? Often there's a very specific format in which I want people to submit it. Please pay attention to that, because I'll start deducting points. And the reason is, you'll notice there's a lot of you. Okay? And it's a lot of people to grade. And if everyone's submitting homework in different formats, it just makes the TA tear their hair out, and it makes their job take twice as long. Okay? So if you want your grades returned fast, we're going to have to follow a format. Okay? All right? Again, you can talk to other students. You can work in groups, but just don't copy each other. Okay? They'll have a math component and a coding component. All right. Quizzes. There will be in-person quizzes. I will always announce them. They will be on the schedule when the schedule is posted. And if there's a change in the schedule, just keep an eye on the schedule. All right? They'll always be announced. And it's to check on the concepts. You won't be doing a lot of hard math on the quizzes. It's to make sure that you're following along with the concepts. It's about 20% overall. We typically do about 5 quizzes a semester. Okay. All right, exams, 20% each. There are 2 of them. We have 2 exams. The exam review lecture will happen before every exam. Before every exam, we'll have a whole lecture that's just review. All right? Okay, about 5, 6 problems, an extra one if you're a grad student. So it's a little harder. They're like traditional pen and paper exams. They still do those, right? Okay. Again, it's to make sure that you can do the core math associated with control systems. All right? Okay, there is no final. No final exam. Okay, instead we're having a project. All right? Where you apply control systems to a project of your choice. Your choice. And you're going to work in a group. Okay? Otherwise, we'd be grading 70 projects. That's a lot. So, all right, groups of 2 to 3, we're going to up that to 4 to 5 with the size of this class here. All right, and the idea is you get to choose what you want to control, and it can be something you find fun, or it can be something you're doing for research. Anyone working on research projects or a thesis or anything like that? Some people working on. Some people, yeah. Some grad students here. Probably doing research. A lot of you are doing research, right? Is it okay for you to use your research project as a control systems project? Absolutely. I want that. I want you to apply what you're using to your actual research. That'd be amazing. So if it helps you in your research, that's awesome. Go for it, okay? You'll choose your groups. We'll have a group pairing session sometime in the near future, next couple of lectures. And we will divide up the project into a couple of deliverables. There will be a proposal phase where you say, oh, here are a couple of ideas. Oh, I want to control a simulation of a robot of a Segway. Do people know what Segways are still? Do people still? Something different. Something different.
Oh, the one that goes on the rails like it's a...
No. You're thinking of something else. You're thinking you're trying. Want to try again? No, it's all right. Try again. No, it's the thing. It's the little thing you ride around. It has 2 wheels, and you lean forward, lean backward, and it's the mall cop vehicle. That's better known. Paul Blart's mall Segway, right? That's it. I want to control a Segway, and to be clear, you do not have to control a physical device in the real world. We will teach you how to do computer simulations, and you can control computer simulation. If you want to control something. A physical device. If you happen to know how to program a Segway and you have one, good luck. That's awesome. In fact, I have a policy. I call it my Dare to be Awesome policy. Okay, that if you try to do something awesome, I will. That will get you some bonus points. Okay, you know, I love the classes are an awesome time to be ambitious, right? I mean, no one's feelings get hurt except, you know, I guess if your grade gets hurt. But my point is, I'm trying to protect your grade. You know, so it's a good time to try awesome things that fail, right? You still want to get something to work for the project, but there are things that you can get working that are short of your goal. And certainly, I will advise people that if you have an ambitious project, I would say, oh, start with a simple version of it first, then build up to something complex. But if you want to do something awesome, I totally encourage it. Actually, one year I had a student, they made a lamp. And it was a lamp that had a light bulb in it. It's like a little Pixar lamp. Except the light bulb didn't screw in. The light bulb was levitating underneath the lampshade. And how? There was a little electromagnetic coil that would control the position of the light bulb, so it was just floating there, and at the same time power the light bulb. And he made a controller for it, for the class. That was awesome. Okay? You do not have to do that to get an A, but by all means, if you want to, or if you want to apply to a real project, if you're working in the fluid systems, if you're working in like an aerospace lab, you're like, I'm going to do a control system for this thing in a wind tunnel. That's awesome. Go for it. Okay? We'll be coding in MATLAB for this class. Who here has used MATLAB? Okay, all right. Fantastic. MATLAB has excellent control system toolboxes. Actually, it's called the Control System Toolbox. It's well named. Okay? So, and it's still a standard for how people do control systems. In my other class, we'll be using Python. Python is still popular, but anything that you can do in MATLAB, theoretically, you can do in any other language, right? But this is where there's a lot of support in the textbook, and you all have a MATLAB license. And that's good. That's good. So, that's the outline of the course. Any questions so far? No? Yes? Question?
Are you going to deal with like drone controls?
So, are we going to deal with drone controls? Well, not drone controls specifically, but if you want to do a drone control project, people have done drone control projects. All right? Yeah. Other questions? Okay. So let's get a little bit into the meat of this material here. Let's talk about control. Let's talk about control a little bit. All right? Now, I work in robotics. People talk to me about control all the time. But really what they're asking me when they ask me that question is it AI? You have a robot moving around, is that AI? If you have a power plant that's controlling the temperature or the flow rate of an output, is that AI? And that's a complicated question. Depends on what they mean. Because what people think is they think some kind of crazy, sophisticated computer neural network that's like the brain when they think AI. But in reality, in a more formal definition of AI, is much more broad. The AI is anything where you have a computer making a decision as opposed to a person. It's artificially intelligent. The thermostat in this room that is thankfully trying to control the floor to heat down to something manageable, right? That's making decisions on our behalf. Technically, it's AI. Now, that's not typically what people mean by AI these days. They mean ChatGPT. They mean something that's going to make a picture of you as an astronaut on the moon, something like that. That's what they mean. But in the grand scheme of things, this is artificial intelligence. So when people ask me it's AI, I was like, well, probably not in the way that you're thinking, but yes. Okay? When in fact, AI, if you go down from we have this Euler diagram here, where AI is anything where it's a computer making a decision for you. Machine learning is learning from data. Guess what? We don't need to do that in control systems. Okay? We don't need to learn from data. If we just know what our system is, we can do some math and we can make a controller that works. We don't need data from the machine to do that. Therefore, we don't need deep learning. That's our neural networks that you see. And foundation models, that's the generative AI stuff. If you want to sound cool to your friends and they're talking about AI, it's like, oh, you just casually call them foundation models. They won't know what you're talking about, but it's the same thing. But they'll be like, oh, that person they must know what they're talking about. Foundation models. So foundation models, that's like a ChatGPT. That's an image generator. Okay? All right, but you don't have to do any of that to do control. In fact, in general, people assume control is code, computer code. And yes, we will be doing computer code, so you're not wrong to think that. But it is much broader than that, okay? When we think about control, we won't be talking first in terms of computer code. We'll be talking instead about things like this. This is a block diagram. These are the kinds of things we'll be drawing, where you have some input and some output, and in the middle is some control, some controller that decides what to do. And that can take all kinds of forms. It doesn't need to be code. One of the earliest control systems, as they'll talk about in your textbook, is a water leveling system. Your toilet has a controller in it. Now, a computer, unless it's a fancy toilet, fancier than my toilet, but there's a little bob that bobs up and down that reads the level of the toilet and opens up the valve to let the water rush in, rush out. That's a controller with no code. Okay? All right? And the idea is we take that controller and we hook it up to, this controller puts out an effort to, I call it a robot, but guess what? This course is about way more than robots. And I apologize in advance if I talk about robots too much. I'll try to shoehorn in as many non-robot examples as possible. But literally, anything. You want to control an airplane. That's a controller. All right? You're working in the thermofluid side. You have a power plant, a turbine. That's a controller. All right? The heat in this room, that's a controller. Pipe flow, you need a controller. Okay? All right? And so we have a more general word for something that's like the physical thing you want to control. It's called the plant. Not like a potted plant. Think of it more like a power plant. But it's called the plant. All right, and out of that comes out what it does. So you send in effort into a thing, and then it does something. It actually does something. But in control, what we typically want to do is say, hey, that thing that we did, is it what we wanted? In fact, let's take that signal, that little arrow, they're called signals, all right? Let's take it back to the beginning of this process by measuring it with a sensor and compare it to this thing at the beginning, this arrow right here, which is what we want, the desired. So you see that little circle with the plus and the minus? It's called a summing junction because it sums, right? Take what you want, desired, subtract out what you got, desired minus actual, okay? That has a word, it's called error. We're seeing that a lot in this class. And it's not just the red text that your programming language gives you when you screw up, okay? It's how far off you are. And you could think of control as being all about driving that error to what number, friends? Zero. Zero, right? And in fact, controls is often seen primarily as a mathematical discipline, not a computational discipline. Because there's a lot of math that goes into showing that, yes, in this system, if I have this kind of controller, my error will go to zero. Or even say, hey, it won't go too far away from zero. Or say exactly how far away from zero it's going to be. All right? And that's the kind of math we're going to do in this class. In a way, you can think about controls as trying to find zero, despite all the complexities of what your plant, your physical system, is like. Okay? So this is what the controller is at the end of the day. In goes an error, out goes an effort. Okay? Not the only way, but that's the most common way. All right? That little loop you saw in that diagram, we call that kind of control a closed loop controller because it's a closed loop, right? And we'll go into more of these definitions more next lecture. I'm just giving you an overview of the kind of things that you expect to see in this class. So the idea is that, that the effort is some function of your error, okay? Your effort is equal to something, something error. Who gets to choose what that function is? We do. Yeah. You specifically, sir. You raised your hand. No, you did. You participated. Thank you. Okay. You're great. We choose what that is. As controls engineers, that system, that plant, it is what it is. Believe me, I worked on enough projects where the control people are like, hey, they're talking to the physical system people, the designers are like, it'd be really great. They're like, it'd be really great if we had more torque on our motors. And then the design people laugh. It's like, you wish, right? You've got what you got, right? Oh, it'd be nice if the robot was lighter. Good luck with that. Drill holes in it, you know. But you have what you have as control engineers, and you got to deal with it. So we get to choose what that controller is. We choose it. All right. And you can see that, and you can see these types of controllers in all kinds of things. This is just a little animatronic device. Let's see if we can get this. It's a little animatronic here. Oh, look at that. Whoever. It's cute, right? Oh, look how fancy and smart it looks, right? Well, what's controlling this thing what's actuating this thing, I should say, are servo motors. Who's ever seen a little servo motor before? Okay, yeah. They're really nice. If you ever use a servo motor, you just say, hey, I want that little wheel, see those little wheels there? They spin to a position, right? I want it to go to this position, and it'll just go there. Oh, that's nice. Super easy. Controls is easy. But how does it do that? Well, I gotta show a video of it. How about that? Isn't that nice? How thoughtful of me to provide a video. Okay? Well, what it does, if you go and look at the actual manual for that motor, you see something like this. You see little arrows going around. Those are signals. The blocks, you have those blocks in the block diagram. Those are called systems or subsystems. Something like that. That's what the controller is. You notice they're not providing lines of code. Lines of code is to what's in there. This is what they give you. And this is what you're supposed to understand what it does as a controls engineer. And you'll see there are blocks, and they have little math symbols in there. Little KV, P, all that stuff. I imagine some of you know what that means. Anyone have an idea what's going on in there? Yeah, some people are saying proportional integral terms. Yep, you're getting to the right thing here. That's right. So what we will understand in this class is how to know what to put in those blocks so it makes our controller behave in a way that we want. And then learn how to put it in code. All right? And this works for more complicated systems than just those little servos, okay? Here we have, this is down the hall. This is my laboratory. This was our robot Cassie. And this is just walking around, and my student creates a little keep out zone. That's that little cartoon circle that we put there. And it's walking around, it's trying to keep out of the keep out zone while it's kind of being restrained like that, right? So very sophisticated controller. There's a lot of stuff going on in there. Certainly very sophisticated, and like if you took my optimal controls class, you'll cover more techniques that make it go, right? Okay? But if you go into the actual paper we published on this, you'll see some familiar looking things. That little DES, anyone want to guess what that means? Desired. Desired. Current, that means actual. Okay? Desired minus actual, that's our error. At the core, that's what's happening. As sophisticated and as much going on under the hood, and there's a lot going on under the hood, that's a huge part of what makes it go. So what I'm trying to say is that this math is relevant even in very recent research, even more recent than this, I would say. Okay? Here's another example. This is my student trying to get Cassie to balance. And you can see this blue circle. That's where its center of mass is. And the little white circle that's sort of hiding behind the blue circle, that's where it wants to be, desired minus actual. He has a feedback controller, proportional derivative controller in this case, that's trying to get it, that even though he's moving the foot beneath it, it's trying to balance like that, right? Okay. Even robots like this. This is the Animal robot, developed at ETH in Zurich in Switzerland. They have a fantastic robotics program there. A colleague of mine named Marco Hutter and his group did a lot of work in pioneering how to make four-legged robots walk around using AI, specifically deep reinforcement learning, which that's not part of this class. That's another class. I have a machine learning class next term in case you're curious, right? But if you go into the paper where they published on how they did this, okay, they talk about, oh, look, we use these computer simulations. We use it to train a deep reinforcement learning model, and we will learn to build computer simulations in this class, friends. Don't you worry, okay? They won't be quite as sophisticated as this, but they'll be the foundations for what makes these work, okay? But then you go further into the paper, and they'll have these diagrams, all right? You look there. It's one of those controllers, a proportional derivative controller on error. At the core of it, as sophisticated as this is a major paper, changed the face of robotics. It's all in there, okay? Further, Got plenty of other stuff going on here. All right. So, sorry, I'm losing track of my slides here. So, and again, I'm just using robot examples because I'm very familiar with them. But it's not just robot examples. It's not even just physical machines. Okay, I remember in grad school, I was listening to I think Science Friday with Ira Flato as a podcast. They had podcasts back then. Okay, and he was talking to a cancer researcher who researched chemotherapy. And he was talking about how they were experimenting with new chemotherapy regimens. There was this really fancy way where this really fancy approach where they used, where the idea was that in certain types of cancers, that if you tried to give the maximum dose of chemotherapy to a patient or an animal model of a patient, okay, still wouldn't survive. You know, the cancer is too robust, right? But then they looked carefully at what was happening inside of the system, the plant, if you will. Right? And notice that there were not just one type of population of cancer cells. There were multiple types of populations of cancer cells that were competing for resources. And so what they hypothesized was that, hey, maybe by putting in maximum chemotherapy, what it's doing is it's killing off the most vulnerable of the cancer cells in that population to chemotherapy, and then removes the competition from these other cells. And then those cells take over, and then you can't stop the cancer, right? So what if we had a measured and controlled way to deliver the right amount of chemotherapy over time to keep the certain population of cancer cells alive in a way that that sort of shrinks down the total population of all cancers at the same time without killing off one of the populations? And you know what he used? Control systems math to figure out how much of a dose of chemotherapy to give. And that was part of the paper. I was like, that's a whole field. It turns out there's an entire field in optimal control of chemotherapy. So as much as I will use these robot examples because they're very engaging, to me at least, right? They can apply to many different types of problems. So keep an open mind when you're thinking about your projects as to what you can apply them to. So any questions so far? All right. How are we doing on time? I think it makes sense to pick up next time. I'll meet you on Thursday. I'll be right here. We're going to discuss Chapter 1's materials from the Norman Nye textbook, okay? And we'll move on from there. Have a good one.